video, we're going to be working with our third method for solving a hypothesis testing questions where we're testing two means. Here we're going to use the confidence interval approach. And to work through this, we're going to use practice problem number 20 on page 460. So here we are going to be looking at using a significance level of 0.05, and we're going to be testing the claim about the mean amount of strontium 90 in the water comparing for PA residents as compared to New York residents. So this particular type of problem we're looking at is exactly what was used early on in the on-site studies at Flint, Michigan, and other places where they're now testing for lead in the water. These would be used on-site to be able to identify areas that they would then go in and do more focused and detailed testing on. So that's exactly the approach that we're using here. And if you look on the slide, you can see that I've actually put the data for you up here as well. So the data that's represented in your book, I've also put up here on the slide for you to work with. So the first thing you're going to want to do is pause the video here and go open your Stats Crunch and enter your data in with two different columns, one for PA and one for New York. Make sure you label them so you know which one is which when you get your when you proceed forward. Then when you have that set up, turn the video back on and we'll go through the steps over here to the right together. Make sure that you're taking the time to get your data in correctly. Whenever you're entering data for a problem, entering data incorrectly is one of the leading contributors to getting an incorrect answer. So pause the video here, get your Stats Crunch open, enter all your data carefully. Then once you've got that set, turn the video back on and we'll proceed through the steps together. Okay, now, as always, the first thing we need to do is check our requirements and make sure we're using the appropriate test. So if we're looking at this particular problem here, we can see that the simple random sample is assumed. We're also told to assume that the sample as populations are normally distributed. So although we don't have a sample size of 30 or greater, we're told in the problem to assume that they are normally distributed. And as we can see here with our Pennsylvania and New York residents, there's no reason to think that they might be related to each other. So we're doing an independent samples t-test here. So once we've checked our requirements, the next thing we need to do is identify the specific claims and set them up symbolically so we can make our hypotheses formula. So here we can see they're being asked to solve for the problem of the PA residents being greater than the mean amount of the New York residents. So that tells us that looking at number 3, our solution step is going to be mu1 greater than mu2. Okay, so once we have that set, and we know that that's going to be for our option 3, that's the alternative claim that we're going to be working with, we can come up and then see that, of course, here we're going to have our mu1 is equal to mu2, since that would be the baseline of nothing if there was no difference between the groups, if there was no meaningful change. So once we have that, again, the last step here on this page is number 4, putting them in terms of the hypothesis formula and identifying our mu1 equals mu2 is going to be our null hypothesis, and our mu1 being greater than mu2 is our alternative hypothesis. So once we have that set, we're going to move on to our next steps, which is going to be here finding the value of E representing our margin of error. So we're going to use the formula represented here for solving this for this particular value. So you can see here when you're looking at this, most of these pieces should be familiar to you already. Your N being your sample sizes, your S being the standard deviation for your samples. The symbol we have here, however, with the T with the subset alpha divided by 2. Keep in mind that is a symbol. It represents your T critical value at your particular selected alpha. It is not a calculation formula. Do not try to take your alpha and divide it by 2 or do some form of calculation with it. That entire image right there is a symbol. So we need to determine our critical value. What do we need to do to determine the critical T value here? We're going to need 3 things. What are they? We're going to be my degrees of freedom, alpha, and I need to know if it's a left, right, or a two-tailed test. So when looking at the degrees of freedom, both of our groups have the same sample size of 12. So we're going to be looking at 12 minus 1, which gives us a degrees of freedom of 11. Our alpha we're going to get from our significance level, so that is going to be 0.05. And the last thing we need to do is determine whether we have a left, a right, or a two-tailed test. So looking at the language cues that I've given you previously, we're solving for a greater than problem. What type of tail test do we solve for here? Well, we're going to be solving for a right tail test. If that's not clear for you, go back to the previous videos on confidence using a critical value and pay attention to the language and how we use the language in the alternative hypothesis to determine which tail type test we've got. So pause the video here, go look this up so you can make sure you can locate your T critical values appropriately. So you're going to be looking at degrees of freedom of 11, you're going to be working with a one tail test, and you're going to be looking for the alpha 0.05. So pause the video and look that number up. When you've got your T critical value located correctly, turn the video back on and we'll work from there. Okay, you should have got 1.796 for your T critical value. So we're going to take that value, and keep in mind here it's only a positive because we're solving a right tail test. So if we were solving a two tail test, it would be a positive and a negative, remember, because we'd put them on either side. But here we only have one T critical value. So we plug that into our formula. And next we need to solve for our S's. Now we can solve for our S's using this formula up here at the top left hand side. This is in fact exactly the formula we learned all the way back at the beginning of the semester when we were doing our calculations for our summary statistics. So you can use that formula again just as we did there, or you can use your stats crunch. So if you're using your stats crunch, you're going to want to go in and go to stats, open summary stats, then you're going to want to select your two columns, click next, and then you're going to click calculate. Once you do that, you should get your summary statistics for both of your columns. So that will include telling you what your N is, which you already know already, also along with what is your S for each of the two groups, and also your mean. So once you have those values, pause the video here, go through those steps, and then plug them into this equation that we've been building. Once you have that set, turn the video back on and we'll proceed together. Okay, so here would be the equation once we've plugged the numbers in. Pause the video here, make sure you can go through and do these calculations correctly for getting your final E. Once you have that correct, turn the video back on and let's check it together. Now you should have gotten a final E of 6.142. So this will be your final E value that we have that we're going to be proceeding forward in the problem. So here we have E 6.142, and our next step is finding our confidence interval. And we're going to use our E for that calculation. So here's the formula that we use for finding our confidence interval. Now notice the similarities in this. This is just like the confidence interval formulas we used earlier in the semester where we were doing a single sample, except for here, instead of using the mean of that sample, we use the difference between the mean of the two samples. So we're going to have the mean of X of population 1 minus the mean of sample 2. So keep that in mind when you're looking at this. This is basically exactly the exact same formula we've used before, except for instead of a single mean, we're using the difference between the two means. So you're going to want to plug these in as you got them from your stats crunch when using your calculating your summary statistics. So pause the video here, plug those numbers in, and do your computations to find your confidence interval, and then turn the video back on and we'll check it together. Alright, you should have gotten a formula that looks like this with your original numbers plugged in, and then going through, you should be getting a final confidence interval of 5 and 17.3. So we're going to be looking at our difference of our mu1 and mu2 is going to be greater than 5.0 and less than 17.3. So now that we have that set, what is the next step I've got to do? What is our next step in solving this problem, pulling from the hypothesis testing steps we've been using so far? Well, it's going to be assessing the rejection. So if if the confidence interval does not contain the claimed value of the population parameter in the HO, in the null, then we're going to reject it. We're going to fail to reject it if it does contain the claimed value. So let's take a look at that in a little bit more detail. So here we see, first of all, starting off again, looking back at our null and our alternative hypothesis that we're working with. And it's important again to bring these down so that you can make sure you're making the correct assessments. So if my null hypothesis was true, then mu1 minus mu2 would equal 0. So when we're looking at making our assessment, the null hypothesis is claiming that 0 would lie within the confidence interval parameters. So if it's true, then we would find 0 within our confidence interval. Now remember, we are testing the null here. So although we're interested in the alternative, when we're talking about what we're actually testing, we are testing the null. So we always test the null, and we reject or fail to reject the null. All right, so looking at this, then we need to ask ourselves, does our confidence interval contain 0? And if it does contain 0, then we fail to reject the null. It's possible then that value is within there, and thus the null is correct. If no, then we do reject the null hypothesis. So looking at this, do we reject the null or fail to reject the null for this particular problem? So it does not contain 0, so we are going to reject our null hypothesis. So here we have this set up. Our confidence interval does not contain the value of the population parameter claimed in the HO in the null hypothesis. Therefore, we reject the null hypothesis. And we need to restate our decision in non-technical terms to address the original claim. Once again, we're pulling up and looking at our hypotheses here, so we can make sure we're stating it correctly in terms of them. And here is the statement that we would use for restating these results. And if you're looking at this, notice your text also has another version of it. If you look over on page, I'm looking very quickly because I don't have it in front of me at this very exact moment. Here we are, page 452. So if you look at that particular sample that they give you, again, they're taking you through the same steps we've done here. So this is always great if you're following the video and you're not quite sure with it, you want to go through a different example of it. Keep in mind your book has other examples. I do not use the same ones your book has. So that allows you to have two different ways of working through the problem. And at the bottom, you can see the interpretation in terms of the language. So here we're saying that we are 90% confident that the limits of 5 and 17.3 actually do contain the differences between the two population means. Now keep in mind we're saying 90% because remember when we're looking at our confidence intervals, we need to pay attention to our computations. If it's a two-tailed test, then my confidence interval equals 1 minus alpha. If it's a one-tailed test, such as we have here, then my confidence interval is 1 minus 2 times alpha. Okay, because remember when we're looking at this, we've got, when we're looking at the two-tailed test, we're having that on both sides. Here on the one tail, we've only got it on the one side. So we need to pay attention to that and multiply that by 2. So here, when we're looking at, we have a 90% confidence that the limits of 5.0 and 17.3 actually do contain the difference between the two population means. Okay, because those limits do not contain 0, the claimed value of the population parameter in the null, this confidence interval suggests that there is a significant difference between the two means. Because the confidence interval consists entirely of positive values, there is sufficient evidence to support the claim that the PA residents have a higher level of strontium-9 than the New York residents. So notice the different steps that we have in here. First, we're saying what is our confidence interval, setting the parameters of it, and we're saying how confident we are that the difference between the two means actually lies within that range. Now keep in mind, this is 90% confident. There's still a 10% chance that we're wrong, but we're 90% confident here. Then we move into the next step where we're rephrasing exactly what we just did in step 7, looking at the limits and whether or not they contain the claimed value from the null hypothesis, which in this case is 0. So that suggests since it does not contain it, we reject the null hypothesis and we infer that there is a meaningful difference between the two means. Because the confidence interval contains only positive values, keeping in mind we're subtracting mu2 from mu1, that would mean that mu1 would always be larger than mu2 in order for getting these positive values. There is sufficient evidence to support the claim that the PA residents have a higher level. So, and keep in mind when we're looking at this alteration for the 9% confidence interval, this is already incorporated into the t-distribution table, but we're doing a confidence interval, we have to do it ourselves. Now, lastly, let's take a look at how you can do this with your stats crunch. So again, going under stats, t-stats, to sample, and data. When you open this up, you're going to get this particular dialog box. So make sure here when you're looking at this now, you're not solving for hypotheses tests, you're doing a confidence interval, and you need to make sure that you are setting the appropriate confidence interval level. So keep in mind here, looking at the way this is set up in the stats crunch, you do not specify one or two tail tests. So you have to use the formulas here yourself. This is the same formula I used for doing our interpretation at the end when we were doing it manually, but now we need to do it earlier on in the steps because we need to make sure we're entering in the correct confidence interval. So here, for this particular problem, we're going to set it for 0.90. So once again, remember, if you've got a one-tail test, you cannot set your confidence interval calculated directly from your alpha. You're going to have to take your significance level. You're going to have to take that, multiply it by 2, and then subtract that by 1. Let's also be very careful that you're turning off your pooled variances. We are not pooling our variances in these problems because we are assuming that sigma 1 and sigma 2 are not equal in the overall population. So once you've taken that step, do your calculation, you should get an output that looks something like this. So you can see here is our intervals. These are a little bit different from stats crunch due to the rounding factors and hand calculations. So do be careful in your homeworks and your exams when they're telling you to use technology or not use technology. That can produce a slight important difference. I will tell you the degrees of freedom of 15.99, I am honestly not sure where that is getting that from. However, so do not use that obviously for when you're getting your degrees of freedom, you need to calculate that yourself. That concludes this particular lecture. Thank you.